Welcome to The Explainer. I am absolutely thrilled to have you here today. We're embarking on a really fascinating journey, exploring exactly how we capture and measure the physical world around us. We're going to zoom all the way out to look at massive architectural plans, and then we're going to zoom all the way in to look at the minute imperfections of physics lab measurements. The whole shebang is about proportion, precision, and the hidden realities of data. So let's start with a massive macro challenge. Have you ever wondered how we managed to fit an entire towering skyscraper onto a single standard sheet of paper? It kind of seems like magic, right? But it's actually a highly structured mathematical language. Okay, let's dive into this. The answer is architectural scale. Essentially, this is the process of shrinking real-life objects proportionally for a drawing or a model, using a very specific ratio. This isn't just about making a pretty picture. It's absolutely crucial for making a document that builders can actually use to construct designs accurately. By reducing reality down to these exact proportional ratios, architects ensure that every doorway, every window, and every single beam is perfectly represented. Here is our quick roadmap for the explainer. 1. Shrinking reality to scale. 2. Speaking the industry language. 3. Pushing measurement to limits. 4. The principle of moments. 5. Graphing the uncertainty. And finally, 6. The reality of physical variables. All right, Section 1, shrinking reality to scale, specifically the 1:100 ratio. Let's see how this builds our understanding of spatial representation as we shrink reality down to the page. The crucial point here is wrapping your head around the basic ratio concept. In a 1:100 scale drawing, a tiny 1 millimeter line drawn on the paper represents a full 100 millimeters out there in the real world. You were literally shrinking the object by a factor of 100. So when professionals say something is drawn to scale, they mean it strictly and ruthlessly adheres to these mathematical proportions. There is absolutely zero guessing involved. Moving right along to Section 2, speaking the industry language, metric versus imperial. You know, scale is the foundational language in design, and you can't just go inventing your own grammar. Making up random scales is a major rookie mistake. You've got two main dialects. First, the metric system, which uses millimeters and meters, completely avoiding centimeters in architectural drawings. This is used in most of the world. Then there's the imperial system, relying on feet and inches, which is still the standard in the US. What's really vital here is how you speak it. A colon is pronounced 2, as in 1:100. And in imperial, the equal sign is also read as 2, like 3 inches to a foot. Knowing how to actually say it makes you sound like a true industry insider. So which scales do we actually use day to day? Because we definitely don't use everything. A brilliant way to memorize standard metric scales is to think of common coin denominations. We use 1:1, 1:2, 1:5, 1:10, and so on, perfectly mirroring coins from a penny all the way up to a £2 or euro coin. You'll notice scales like 1:30 or 1:40 are completely skipped over. We stick to these accepted standards so everyone on a construction site instantly understands the math, without any confusion. All right, Section 3, pushing measurement to limits, the least count. Let's shift gears completely. We are stepping out of the macro world of architectural drafting and into the microscopic precision of the physics lab. Here's a foundational term you absolutely must know, the least count. This is the absolute smallest measurement that you can accurately make with a specific instrument. Think about a standard plastic ruler on your desk. It has little lines spaced 1 millimeter, or 0.1 centimeters apart. You physically cannot measure lengths with that standard ruler with an accuracy any better than 0.1 centimeters. That is its physical limit. But what if we want to bypass that physical limit? Well, we can actually use geometry. Here's an amazing DIY experiment from the lab sources. We're going to make a paper scale that lets us read fractions of a centimeter without needing those tiny, impossible-to-draw millimeter lines. First, we draw a 30-centimeter line, mark it every 1 centimeter, and draw perpendicular lines. Then the magic really happens. We draw parallel lines above it, and we slash a diagonal line right across those parallels. This diagonal effectively stretches out the 1 centimeter gap, allowing us to accurately read increments of exactly 0.2 centimeters. Pretty clever, right? And this brilliantly illustrates the concept in action. We've placed a pencil on our custom paper scale. The pencil obviously goes past the 3 centimeter mark, but where exactly does the tip end? By following the tip up to where it hits that diagonal line intersecting with our parallel grid, our eye can easily and accurately read the fractional part. It hits the second parallel line up, giving us exactly 3.4 centimeters. We just bypass the limits of a standard ruler using pure geometry. Section 4. The principle of moments, balancing physical space. Let's step off the flat 2D paper and into 3D physical space. To measure unknown masses, we rely on the equilibrium rule. For a balanced body, the sum of clockwise moments equals the sum of anti-clockwise moments. In plain terms, if you have a seesaw, a known mass times its distance from the center on one side will perfectly equal the unknown mass times its distance on the other side. So m1 times L1 equals m2 times L2. Let's visualize this real-world lab setup for a second. We have a wooden meter scale acting as a beam, balanced perfectly horizontally on a sharp wooden wedge. On the left side, hanging from a little thread loop, we have an unknown mass. And on the right, we have standard known weights from a weight box. So, how do we actually run the experiment? It's pretty straightforward. First, you balance the bare scale on the wedge to find its exact center of gravity. Second, you suspend your unknown mass on one side and guess a roughly equal known weight for the other side. Third, you carefully slide those thread loops back and forth until the scale balances perfectly horizontal again. Finally, you just measure the distances from the wedge to the loops, plug those numbers into our M1L1 formula, and boom, you've calculated the unknown mass. This hands-on process essentially replicates the exact mechanics hidden inside a commercial physical balance. On to Section 5, graphing the uncertainty, embracing the messiness. Now, what's really interesting about this is facing a hard scientific truth. Absolutely no physical measurement is perfect. Notice the plus or minus 0.1 attached to the values we're tracking here? Whether we're measuring the length of a pendulum or timing its swing with a stopwatch, our instruments have a least count, a hard limit to their precision. When we graph data like this, we don't just plot a single tiny dot. We draw error bars, little lines showing this exact plus or minus range. It visually proves that our measurement is actually a range of probability, not a perfect mathematically exact point. And that brings us to a central truth of our physical world. Every piece of data has some uncertainty or error due to a lack of precision in measurement or some other factors inherent in the process. Despite our absolute best efforts, despite our clever geometry tricks and meticulous lab setups, nothing in the physical world is ever 100% exact. And finally, Section 6, the reality of physical variables, friction, and motion. So what are the real-world variables that constantly mess with our perfect measurements? Well, let's look at friction for a moment. In experiments finding rolling friction, we put a wooden block on a table attached to a pulley and a pan. We slowly add weights to the pan until the block just barely starts moving. That exact moment gives us the limiting rolling friction. But notice how we have to keep adding extra 100-gram weights to see how the friction changes? The physical world resists us. We constantly have to overcome these invisible physical forces just to get our data. And the friction doesn't stop there. Think of the inevitable, frankly annoying sources of error you encounter in any lab setting. You might suffer from parallax error, which is simply looking at your ruler from a slight angle. The very pencil line you draw on your custom scale actually has physical thickness that throws off your fractions. That wooden meter scale we balanced earlier, it might have slightly more moisture or density on one end than the other. The pulley wheel might be a bit rusty, adding unwanted friction. If you're measuring water jets, the tap pressure might fluctuate. All of these physical factors gang up to create the messy uncertainties we've been discussing. We've journeyed from shrinking giant buildings onto paper, down to finding fractions of a millimeter, and finally embracing the inherent errors of our physical universe. So, I want to leave you with this provocative thought. Knowing that every single measurement has a hidden margin of error, what hidden uncertainties exist in the everyday numbers you rely on? Whether it's the square footage of your home or the speedometer in your car, remember to look at the measured world around you with a new, critically precise eye. Thank you so much for joining me on this explainer, and keep questioning the data.